Okay, welcome to another lecture. We're going to be studying, today we'll be looking at the connection between the micro and the macro worlds. So, you probably have some questions here. How is our macro world that we see connected to the micro world of atoms, molecules? We're talking about thermal energy of a system. We've talked about thermal energy, kinetic energy, and potential energy. Is thermal energy really a new form of energy, different from kinetic and potential energy? Last semester when we talked about energy, we talked about potential and kinetic energy of particles. How can we connect this to the pressure and temperature of a gas? Can we? What about solids? Is the temperature of a solid related to the potential and kinetic energy of molecules in the solid? So these are the questions we're trying to look at in today's lecture. So some key points, I think we can divide it basically into two key points. Macro, we can observe pressure, temperature, the number of molecules, the volume, right? And in the micro world, we observe, when we talked about particles, energy was equal to U plus K. And in a transition, so those were basically how we defined energy in the micro world with particles, E equals U plus K, and also for moving objects. Here in gases, we describe the macro P and T. So are these related? And we can find, yes, for ideal gas laws, there is a very simple relationship. The pressure of an ideal gas is equal to 1/3 the number of molecules divided by the volume times the average energy of an individual molecule. The temperature is also related to the average energy of individual molecules. In this case, by the Boltzmann constant, and it's 2/3 the Boltzmann constant. So the key thing here is if I know the number of molecules I have and the volume it's occupying, as long as I know the average amount of energy, I can get both the pressure and the temperature of my gas, both from the average amount of energy. Now, how is this average amount of energy related to the motion? Well, the average amount of energy is related to 1/2 mv RMS squared. What this looks like is related to the kinetic energy. In other words, what we've got now here is, in our molecule, we have a relationship now between the pressure and temperature and the average kinetic energy of each of the molecules. That's the first thing that we're going to be finding out in this today's lecture. The second area we're looking at is the second law of entropy. The second law of entropy is quite interesting. It provides an idea of time. In other words, time can only go one way. Now, when we talked about collisions, we had two laws for particle collisions. One was, if collisions are perfectly elastic, right? We can define, we need to have the same energy before and energy after, same momentum before and momentum after. So individual collisions are reversible. In other words, if I have two particles crashing into each other and then going off different directions, I could equally just reverse the direction and then reverse the time, and the opposite would happen. So these are called reversibles. So for example, if I have one guy coming from the left and one guy coming from the right and they smash into each other and bounce back off, I could then change it and do the exact opposite and have them come in the opposite directions, bounce off each other, and do it the opposite way. The physics would not change. However, when we have many collisions, things become one way. Okay, so let's now look at the PHET, a simulation, so I can try to illustrate this. Let's see. Okay, Okay, I've got 10 particles here. Okay. And I got, say, 40 particles here. Okay, and you can see they're nicely separated here. 10 particles on this side and 40 particles on this side. Now, let's say I remove the divider. Well, particles start to cross. There's an equal probability that a particle will come from the left side to the right side as there is from the right side to the left side per individual particle. But there were more particles on the right side, so more particles moved across from the right side to the left side. So you now can see everything starts to mix together. This is the law of entropy. The law of entropy basically tells me that, hey, if I'm at this point, let's stop. If I start with this sort of a system, I have basically, if I have 40 and 10 particles, I have almost no chance that all 10 blue particles will go on the left side and all 40 particles will get to the right side. No, on average, I'm going to have about almost between 4 and 6 particles on the left side of blue ones, and about 4 to 6 particles on the right side of blue ones. I'm going to have about 20 red particles on the left side and 20 red particles on the right side. Okay, so on average, we're going to basically get the same amount. Everything's going to mix together. That's what entropy is telling us. We're not going to get all the particles of one type suddenly to go to the other side. Let's, okay, I don't know if I can't really decrease. If I wanted to decrease, let's reset, let's restart again. Okay, I start with 10 particles here. What's likely going to happen if I remove the barrier? What is the chance that I'm going to keep having my 10 particles on the left side? I remove the barrier. Remove barrier. There we go. So there's an equal probability a particle from the right side will go to the left side, but there's no particles on the right side before, so all the particles start to move, we start to move across. And if we stop suddenly, we see, okay, we got 4 particles here, 6 particles on this side. Okay, so there's generally things will get mixed up and will go to more disorder. This is the idea of entropy. Let's move back again. And that is what we'll be exploring today. So in the rest of today's lecture, what we're going to do is we will have our Kahoot. After our Kahoot, I will then go through PowerPoints going through this chapter. So that's our format for today.